as I already mentioned in the other talk, that I had been doing open source microcode simulation of HP calculators since 1995, and you all have, almost all of you have probably seen some of the stuff I did. And in about May of 2005, I got the Voyager calculators running in simulation on Nonpareil. And as far as I know, this is the first time that anyone outside of HP had simulated those particular calculators. HP had themselves released for the HP 150 desktop computer, which was 8086 based but was not a PC. They had released a package that included a simulated 12C, and it really ran the 12C microcode. It appears to have been written in probably Microsoft Pascal. They actually had all the Voyagers ported to it, but they only publicly released the 12C. And so in that package, which I analyzed later, after I'd already dumped the ROMs myself, they had done some kind of trivial obfuscation of the ROM image, presumably wanting to not have people messing with it. So I dumped the ROM images on the SPICE calculators and the Voyager by activating the self-test sequence and just passively monitoring the bus with a logic analyzer. So I was not at that time able to get the 10C because the 10C I had was the early construction with the chips down in a plastic frame that I couldn't probe easily with the calculator running. But I had the 11C, 12C, 15C, and 16C ROMs extracted and then immediately started working on them. So there was an interesting thing that those calculators generally had CPU chip, which was a minor variation on the one in the 41C family. The difference being that the 41C, which ran on nominally 6 volts of alkaline batteries, but toward the end of life would be down to close to 4 volts. Well, to run at the speed they did, they needed to have a DC-DC converter, like most HP calculators prior to that time had, that boosted that to about 6.5 volts nominal that the electronics ran on. For the Voyager calculators, they only had 3 button cells, and being that CMOS is scalable in several different ways, one of them was that that variation of the processor would run directly on the battery voltage at nominally 4.5 volts down to about somewhere a little over 3 volts towards the end of life. Chuck McCord, I'm sure, can tell you a lot more detail about that because that's just my minimal knowledge of it. So anyhow, it basically was a nut processor, which I already knew how to simulate, and then there was a second chip in most of those, which was known as an R2D2, and that stood for RAM, ROM, and display driver. So all the memory and the display interface were in that second chip. And so figuring out how that worked was a little bit of a challenge. It wasn't ultimately too difficult, except I did have help from somebody who's known in the community as harassed programmer. And he figured out, when I had the simulation partly working, he figured out that, there's this register at address 8 versus the display registers that were address 9 and 10 decimal, that register in 8, if I implemented it as RAM, then the calculator would not work, which was my first naive approach. And it turned out that I had to make sure that always read as 0, and then the calculator worked. I think that register the calculator writes it before you turn it off, and I think that register has to do with the sleep timer. Normally the calculator goes to light sleep when you don't push any buttons and are not running a program, and at some point that goes into deep sleep if you still haven't done anything. So once we had that register always reading as 0, the calculators worked, and I immediately wanted to see, can I expand the memory of the 15C? So those of you familiar with either the DM15 and 15L from Swiss Micros or the new 15C Collector's Edition know the answer to that is yes. Well, it turned out that harassed programmer and I did the early work on that, and I found where to set the base of the RAM and how to manage the initialization so the right amount got initialized or got cleared when you did a clear registers and so forth. But what I missed, and harassed programmer and J.F. Garnier figured out a few things that I had missed that were necessary in order to make the complex stack and solve and integrate work correctly. So I had the basic functionality where you could have more registers or more program or whatever trade-off between those, but not all the functions of the calculator were working correctly at that point. So those patches that those two gentlemen and I came up with are actually the basis of the extended memory in the 15C Collector's Edition and the Swiss Micros calculators, used in both cases without any acknowledgement of their origin, but that's okay. I'm glad people are actually able to use that now. But my personal favorite in the Voyager series is the 16C, being that I do a lot of computer science sort of stuff. And so I, at that time, attempted to also figure out how can I expand the memory of the 16C. And it turned out that the innards of the 16C microcode are a lot more complicated, having to do with the fact that they allow you to set the word width from 1 to 64 bits. Now internally for the storage, and this is actually described in the manual, but they round the user's selected word width up to the next multiple of 4 bits. So it's 4, 8, 6, 12, 16, et cetera, up to 64. And you may be saying, well, but it's a 56-bit processor with 56-bit memory. How does that work? And it turns out, well, it's a 56-bit processor, but it's really good at manipulating either BCD or hexadecimal digits. And so when you have a word length other than 56 bits, like for instance the default is 16, at 16 you get 3.5 registers per hardware register that's 56 bits. And one of the properties is that if you change the word size, it's documented in the manual how those registers get converted. So for instance, if you're in 16-bit mode and you convert it to 32-bit mode, registers 00 and 01 become the 32-bit register 00. They're concatenated to each other. And for any word sizes that happens. That's going to matter later in my little presentation here. So 17 years later, last year, I started hacking the 16C microcode again. And this time I delved into it deep enough that I figured out how that memory addressing actually worked. And so in the Voyagers, other than the 15C, there are 8 registers in the R2D2 that are down at address 0, and those are typically used, it varies by model, but those are typically used for the stack and scratch and status information and things like that. And then there are 32 registers that start at E0 hexadecimal. They're using 8-bit addressing, even though the processor can do more. And so there are 32 registers from E0 to FF hexadecimal, and that's generally where user registers and the program are stored, and also maybe a little bit more status information. So what had tripped me up in my previous attempt is I was looking for somewhere that loaded E0 and added it to something, and there was no such code in there anywhere. And what it was actually done was they compute the relative address that they want to access for the base of RAM, or an address relative to that base of RAM, and then they effectively do 2 decrements on the upper digit of the 2-digit address. So 00 when it gets decremented twice becomes E0, and so that basically solved that problem. Now there were only 2 instructions there, so if I patch that, I can't actually load a constant and add it to get some different constant. So it occurred to me, okay, well, the easiest things I can get at that point, I can't have the base at 0 because that's where the other internally used registers are, but I could only decrement once and set the base to F0, in which case you'd have even less memory than normal. Or instead of decrementing it, I could increment it once or twice and start the registers at 10 hex or 20 hex, and that gets a lot more registers than usual. Some of you might be aware, either from personal experience or from the forums, that the simulation code that Cyril wrote that is in modern ARM-based 12C and 15C actually implements the full 256 register address space. And it turns out that Swiss Micros did the same thing. And so if I patch that, then the more registers are available. But other problems occurred in the 16C. That was only the beginning of the journey. So it turns out, like the 15C, there are anomalies if you try to get program line numbers too high. The 15C can correctly display line numbers up to 999, and the line 1000 has an issue. On the 16C, it turned out that the line number could only go to 210, and then it starts doing funny things. So I found the code that did that and fixed that. I'm going to gloss over a little bit of this to tell you a few of the things. I mentioned that addressing for registers. And the way they do that computation is say you tell it you want to address register 37. So they multiply 37 by the number of digits in your word size, rounded up to the multiple of 4, and then they have to divide by 14 to get that relative address because each 56-bit native data word has 14 digits in it. And the divide by 14 code was really complicated, and I didn't understand it at first. So long story short, it turns out they used actually a well-known trick, which is to divide by an integer by a constant value of 14. They multiply by the reciprocal in fixed point, and in this case to 16-bit, or their approximation of 16 bits. And it turns out, and none of the things I'm going to talk about in the 16C are bugs, because it was designed to have 203 bytes of user memory, and everything works perfectly for that. It's only when I try to push it past the design limits that I run into anomalies. Their division by 14 with 16 digits of precision for that approximation does not work once you get to about digit position 683 or thereabouts, which cannot happen in a normal memory size 16C. So first I wrote a long division routine, and it worked perfectly. The symptom, by the way, is that with the original routine, every 683 digits, they would skip a digit. And that wouldn't be too terrible, except for the thing that then when you change the word size and the combining occurs, it no longer occurs the way documented in the manual, because you get these extra digits either stuck in or removed. So I wrote the long division routine. It worked perfectly. It needed more memory. The 16C ROM does not have very much extra space in it at all. So in the simulation, I now have to use more than 6K words. I'll get back to that. But the long division routine worked, but I was a little dissatisfied with it because it was slower than the reciprocal division for some cases, and I didn't want to do anything that slowed the 16C down. So after understanding the reciprocal division, I thought, well, at least I can use that same technique and just carry it out using a 20-bit constant instead of 16. And it turned out, I actually amazed myself, and I had to do very thorough testing on this to prove that it worked, but I was able to write the division using the 20-bit constant in a couple fewer words of ROM, and it runs one cycle faster than the original code. So I did not slow the calculator down. I actually sped it up slightly. Now, where it does slow down is that the processor is still fundamentally pretty slow. And so if you put in 1,000 program steps, and then you go to insert or delete a program step at the beginning, oh my, is that slow. And this is because Nonpareil very deliberately runs the calculator at original speed. Nonpareil, most of you are probably aware, was more of a research project than an attempt to have something that one could consider as a product. And so accurately simulating the speed of the original was one of the design goals. It turns out that in a configuration file you can tweak that and run it faster, and so I've been doing that in order to be able to reasonably use the 16C with more memory. So other things that happened, indirect addressing worked fine in integer mode. In floating point mode, the word size is ignored and it's always 56 bits. And indirect addressing, the code was deliberately limited to not have more than 2 digits of addressing. It could only go to register 99, which is more than the 16C has. But now that I can have a lot more, I wanted the indirect addressing to work, so I found the place to change that. And the memory display, oddly enough, you hit FMEM, and it shows how many registers you have and information on program steps. And that was slow enough to be a bit annoying. And it's like, well, how could that be slow? And I looked in, and what they do is they know how many registers are unoccupied, and they divide that by 7 to find out how many program steps I'm confusing a few things here, but fundamentally there's a divide by 7 involved, and that divide by 7 was just repeated subtraction of 7. It was not long division, and so if the number is big, then it has to loop a lot of times subtracting 7 before it gets the answer. So I put in a long division for that, and that meant that now, even with the expanded memory, that hitting FMEM is instantaneous. A problem I have not yet solved is there are only 16 labels, and if you're going to have a 1,000-step program, you probably need more than that. Now there are tricks based on the way the label search works that sometimes labels can be reused, but even so, that's not very many. And there are not enough unused opcodes in the hex table to be able to change that easily, although I do intend to change it. So I'm going to briefly demonstrate this running on nonpareil. I'll plug in the video now. And then I have one more thing beyond that. Now the intention of these changes, I mentioned that the 16C was my favorite of these, and I'm not sure the laptop is working. Oh, here we go. So the other thing I wanted to do was add scientific functions. One moment. And for the scientific functions, you will notice that I have put additional legends on some of these keys up here. It was an observation of somebody on the forums that if I wanted to put in more functions, that there are a bunch of keys, because the 16C is optimized for doing integer arithmetic and in the various number bases, there are a lot of keys that are involved in doing hexadecimal or doing bit operations that don't do anything in floating point. In fact, they are such no-ops in floating point that they do not even terminate digit entry. So if you said 1, 2, left justify, 3, 4 in normal integer mode, the 1, 2 would be taken as a number, and then it would do the left justify, and then it would enter the 3, 4 as a new number. But in floating point mode, if you do 1, 2, left justify, 3, 4, you get 1, 2, 3, 4 as your number. So it turns out in the code, they check for those instructions very early on, and they literally just completely no-op them out, so they do not affect digit entry or anything in floating point mode. And that's done in a table. And I thought, great, now I know where that table is. I can easily subvert that and say, well, if it's in floating point mode, instead of no-opping those, I'll add another table that it branches to in floating point. So getting back to this, what you see here is on the A key, these key assignments are not fixed in stone. These were just what it was convenient to do at the time. I started with the log and exponential functions. So you see we've got log and e to the x, natural log and e to the x on this key, and base 10 log or common log and 10 to the x on this one. We've got y to the x and factorial here, and then sine, cosine, and tangent and their inverses there. Now you'll notice I didn't put the g-shifted functions on the front bezel, the front edge of these keys, because on the real thing, I don't have a way to do that. But I can put an overlay on one of the calculators and change them here. So I did the same thing that HP did on a few of the calculators. Here for sine, cosine, and tangent, you see that they're the yellow or gold, and then they have a blue, superscript -1 for the inverse. And where possible, I did that. I made the inverse, the actual logical inverse. This y to the x and factorial is obviously a counter example, but that's so that I could do them on the overlay. And so I guess I won't actually so much demonstrate that as I'm going to pass a couple things around. Now, one is kind of like I described for the Nixie calculator. I actually made overlays using a printer, an inkjet printer, and printable vinyl, and a cutter, and a C++ program to generate that. Again, I did this in C++. I don't remember if I mentioned in the other talk, because using a graphics program would be too easy and fast, and I don't want easy and fast. I want to really labor over this, suffer for my art. And so I spent an insane amount of time on these C++ programs, and they're still not all that great. If any of you looked at the calculator, the typography on the keys is not the greatest in some areas, and I'm still working on improving that. And it amused me very much when Eric Rechtlin pointed out that, trying to use Unicode combining characters like the X with the hat works very poorly, and you will see that if you come up and look at the Nixie calculator. So I'm going to pass around. I did two test sets of overlays, one for HP and one for Swiss Micros, because the geometry of the keyboard is not the same. And I'll pass these around. You'll see that I printed 4 copies of the overlay legends on each of these. Now, these legends should be on a dark, light on a dark background to match the actual calculator, but I haven't gotten to the point on these. I was working on July before my medical adventure started, so I didn't get to the point of making it a dark background and lighter colored legends or anything, but you can see that I've peeled off the actual overlay for the top one on both of these. And I'm going to go ahead and pass these around so you can just see what they look like. But what I'm also going to do, now the problem with the real 16C is the microcode is in ROM, so I can't easily change that. So what I'm going to do is I'm going to pass around a 12C. This 12C does not do anything unusual. It is a 12C. It just has this overlay that shows 16C shifted, F shifted functions, and for the ones I added, the G shifted as well. It's just to show you that the overlay fits on that. So don't expect it to actually execute any of those functions. But the one I'm going to pass around that you can actually poke at is a Swiss Micro's DM16, and this one has my firmware in it. So this one, those trig functions and such actually work. So I'll pass that around. I imagine it probably should be obvious to everybody how to use those. But during a break or whatever, if anybody has any questions about the operation, I'll be happy to answer them.
Your display blanked out.
Well, we don't need it anymore. So if there are any questions anybody has now, Richard?
I'm not sure. Eric may. Eric, you have a cutter, right? Is that the same idea?
Yes, same thing.
Oh, same. Okay.
Yeah, same brand, slightly different model. Oh, I'm gonna mention now that I've talked about this here, and I've talked about some of these changes in the 16C on the museum forum, so they're not secret. What I haven't ever talked about publicly is how I'm going to make these available to anyone. In theory, since the 15C Collector's Edition has this Easter egg of having a 16 mode, albeit with some bugs, in principle, I could probably contrive some way to run this code in a 15C Collector's Edition, and for the people that have the ability to flash firmware, they would be able to. But I don't currently plan to do that, and I also don't really plan to release the firmware publicly for the Swiss Micros, and the reason for that, and I hope nobody is like horribly disappointed or anything, but the reason for that is I actually want to try to monetize this, and so my plan is actually to buy the calculators, install custom firmware, and actually a little bit of custom hardware too to add some more features I haven't spoken about, and also serve as copy protection, and sell enhanced calculators that have the upgraded firmware. I don't know that there's any huge market for this. Most people probably don't want a 16C that has scientific functions. But the intent all along, I started with the 16 because it's my favorite. The intent is to offer some capabilities like this on the 12C, and if there's any market potential, that's probably where it would be. At some point further in the future, I might open source all the stuff, but not right at the moment. David?
How do you put the firmware on a CE? Obviously, you have to open it up.
The battery compartment has 6 little contacts in it.
Okay.
Hey,
Richard?
a place in Spain may be selling those soon.
Okay, good.
I remember vaguely the way that HP treated their development and release of their models, that they didn't patent some of them, and then some of them they did. But regardless, if they did patent them, isn't 20 years?
Patents are up. If they had copyrights on the firmware, those would still be in force. To the best of my knowledge, and I'm not a lawyer, so do not take anything whatsoever that I say as legal advice. To the best of my knowledge, the firmware in the Voyager calculators is not copyrighted. They were published before 1989 when the U.S. became signatory to the Berne Copyright Convention, and prior to that time, anything that you published that you intended to claim copyright on, it had to bear a copyright notice. There were very limited provisions that if you accidentally released a few of something by mistake, and the law doesn't define exactly what a few is, but if you released a few of them by mistake and made a good faith effort to correct that omission, you could maintain copyright. I do not believe that happened in this case. Years ago, I worked, so in 1995 when I started this odyssey of trying to simulate the calculators, the one person I knew of at Corvallis Division was Bill Wicks, and I had no idea whether he would be involved in the least bit in any of this, but I thought he would at least know who to talk to. So I called him up and explained what I was trying to do, and that I wanted rights to distribute the firmware of old calculators for historical purposes only. I was willing to promise no commercial use, for historical purposes as a part of documenting that history. And who would I need to talk to get permission? And he sounded a little bit dejected, and he told me, well, if you had called me 2 weeks earlier, I could have given you that permission. It turns out this was immediately after all authority was transferred to Singapore. And he said, you're going to have to talk to, is it King Ju Cha? Is that the name? Or whoever it was, the head of Singapore. And at a conference, I talked to the head of Singapore, and he thought it was an interesting idea, and he thought he could get the lawyers to take a look at it. And nothing ever happened. And Authority for Calculators moved to Australia, and the head of Australia division was interested and said he could talk to the lawyers and maybe get something to happen, and nothing did. And moved to San Diego and so forth. And at some point when I realized there probably isn't a copyright on those at all, I decided, okay, well, I tried getting permission and it was not forthcoming, and now I'm just going to do it. And is HP going to sue me into oblivion? Well, they could if they wanted to, whether I have a leg to stand on or not. That would be irrelevant. But the reality is that no, they don't really care about this stuff. Now, I did not at any point back in that time, I did not at any point release the 12C firmware, which was a going concern. And
that's the one they
and that was the one that I would be, incurring their wrath possibly. But later on, I eventually included the 12C as well. And when at a previous conference some years ago, when Cyril, the people at HP knew at least some of them knew I had done this. Cyril certainly did. And when I asserted that I did not believe HP had any copyright on it, Cyril got really indignant. And his attitude, he didn't specifically say, but he got visibly indignant. And he said, "Oh, of course we do." And apparently, HP Legal was consulted, and apparently, I don't know if they made any formal statement, but the word apparently got back to Cyril that, well, yeah, nothing's going to be done about it.
But if they did have copyright, it had to be registered.
It no longer does. That's a different issue. The registration requirement in the U.S. was never necessary, or at least it hasn't been for many, many years. It was never actually necessary to register your copyright. But what happened was, if you didn't register your copyright, you could only sue for actual damages. Whereas if you registered your copyright, you could sue for statutory damages, which could be a whole lot more. Statutory damages could be $150,000 per count, which is a lot more than actual damage of I gave somebody a calculator that illegally has a copy of the firmware. So, are there any other questions? Okay, well, thank you very much.